Hello, everyone. So in the next 20 minutes, we're going to be talking about the role of programmable cryptography in DIAC. Programmable cryptography has been talked about in this conference in relation to Ethereum consistent protocols and trust minimization. And I just want to perhaps set the stage to say that cryptography is fundamentally about trust minimization. And there is a new category, a new wave of cryptographic schemes that can help us better minimize trust in different settings. And maybe perhaps the first thing that we'll do here is to introduce our panelist, Muthu. And Muthu has worked for over a decade in cryptography. And maybe can you tell us briefly about your background and your experiences in these cryptographic primitives?
Yeah. Thanks, Wei. My name is Muthu. I'm a professor at Georgetown University and founder of a zero-knowledge company, Ligero. I did my PhD back in 2004 under Rafael Paz, who's a student of Silvio Micali. I've been doing research in zero-knowledge and multi-party computation for, I think, 2 decades now. And I think one of the things for me, just blockchain ecosystem and the Ethereum ecosystem, is that these primitives that we have studied that was discovered in the 80s are really coming to life. But today, I guess, we are going to talk about more advanced primitives, which I would also include like from FHE to FE, witness encryption, and indistinguishability obfuscation.
Yeah, so perhaps let's dive straight into it. So I think most of us here probably have heard ZK, zero knowledge, and MPC, multi-party computation, and perhaps to a certain extent, FHE, right, fully homomorphic encryption. Can you explain the landscape there and also functional encryption, witness encryption, and indistinguishability obfuscation? What do these things actually do?
So when you think of encryption, it is one way to look at it is that with a secret key, you get sort of an all or nothing functionality. If you have the secret key, you can retrieve the entire message. If you don't, you get nothing. These primitives, functional encryption and witness encryption, push these encryption schemes to what we like to call now programmable cryptography. So let's start with witness encryption. So what does witness encryption allow you to do is to encrypt a message with, say, a puzzle. And the idea is that you'd be able to decrypt this encryption only if you know the solution to the puzzle. And this is really beautiful because you don't need to give a secret key to anybody. The secret key is the solution to the puzzle. Now, what could this puzzle be? In the context of, let's say, bitcoins, etc., you could imagine that I want to lock some amount of money for anyone who can solve, say, the Riemann hypothesis. So now you can imagine that anyone who can solve it gets the solution and can decrypt and get a message, which is a transaction paying you some amount. So witness encryption pushes the boundary of encryption to the point where I can now not give a secret key, but just be able to decrypt if I know the solution to a puzzle. Functional encryption and indistinguishability obfuscation, I'd say, is like a little bit of mother of all primitives. Like you can construct one from another and also do a lot of things. So functional encryption allows you to generate like a programmable secret key. This is how I think about it. So what happens is that in a functional encryption, I can encrypt a message, and then I can generate a secret key for a target functionality. And this secret key will allow me to decrypt any encrypted message to reveal just the function applied on the message. So if I say some function f, I can generate a secret key f, that if I hold this, for any ciphertext or any message that's been encrypted in the scheme, I can learn f of m. Now, when this was discovered or when this was defined, etc., one of the classic examples is spam filtering. So I can have the cloud just have a targeted sort of secret key to see whether when an encrypted message or comes to my inbox to do spam filtering. But as we will talk today, you will also see that this functional encryption also has other powerful applications. Now, indistinguishability obfuscation, I would say probably is higher than witness encryption and functional encryption. It actually has this promise that I can take any program and obfuscate, meaning that I can give it to you in a way that you cannot reverse engineer the original code. Now, you should take it with a grain of salt. Pure obfuscation is impossible. So if someone comes and says, hey, can I use indistinguishability obfuscation to replace TEEs? This is not true. So,
yeah, I think there's a lot to unpack there, but continue.
So indistinguishability obfuscation, I want to say, is that it's something that it tries to find the right definition of obfuscation that is both realizable and actually does have meaningful consequences. I'll just stop with the definition of indistinguishability obfuscation. It says that I can obfuscate programs in a way that I will not be able to distinguish the obfuscation of two programs that have identical functionality. And it seems pretty weak, but this form of obfuscation already can give you witness encryption, functional encryption, and a lot of other things.
So just to recap at a high level, if we have obfuscation, then that implies witness encryption and functional encryption. Yeah. What about the other way? Can you briefly summarize the landscape?
So, actually, a strong, again, just like with obfuscation, even functional encryption, there are different definitions. There are different levels of security. If you go for like sometimes the strongest form of security, it becomes impossible. But for a certain kind of functional encryption, actually you can construct indistinguishability obfuscation. So in that sense, I would put both of them in the same category, and both of them imply witness encryption. And going back from witness encryption to these things are harder.
Got it. So witness encryption is kind of the easiest to get, and then functional encryption, I/O, obfuscation could be equivalent, depending on that definition. So perhaps let's zoom in on witness encryption for now. And I think one use case that's really sparked my interest in actually looking at witness encryption is actually being able to extend the existing protocols without actually running MPC. So one example of this is in Ethereum, we'll have BLS signatures, and we'll have already a lot of validators with existing key infrastructure, and the question is, can we actually encrypt to a set of these validators? And there, the condition, right, the puzzle that you described before, will be has enough nodes signed a message, so that you will then be able to decrypt. And so, I think that's one application where people have proposed where we could use witness encryption. So just looking at this particular use case, can you describe to us, is this feasible right now? Do we need custom scheme, or do we need generalized witness encryption?
So, I mean, just probably before the TLDR is that actually this is one of the recent advancements where witness encryption for a specific language can enable exactly this functionality, which is that let's say that I have n signers for something and I want to be able to decrypt something as long as I have, say, T out of n signatures. I can encrypt a message, and the puzzle really is that I need to have T out of n signatures. And there has been a recent construction even implemented to show that this functionality is feasible. But let me just say that general purpose witness encryption would be to ask, can I do this for an arbitrary puzzle? And the answer is, today we only know how to construct that from obfuscation itself. So general purpose witness encryption is still far from being practical, but for this specific application, it is possible to do it. And I want to say that if you also trace history, witness encryption, it goes back to even like when you think of CCA2 encryption, it was a limited form of witness encryption. And since then, there have been some progress, but I want to say general purpose witness encryption is still far way out.
We'll definitely zoom in on that in a later question. But so let's go to functional encryption and obfuscation. I think one of the more recent proposals that applies functional encryption is to actually add features to Bitcoin for it to become more like Ethereum, right? So there's this thing called Bitcoin covenants, which is not feasible on Bitcoin today. And people have been proposing to use functional encryption to get covenants for Bitcoin. And the use case there is to say that ECDSA signing key must be used in a certain way, only if a condition on the signing message is true. So this requires computation on the message to be signed, a condition to be checked, and a signature to be generated as the function to be computed. Can you comment briefly on this particular use case and whether that is feasible currently using obfuscation or functional encryption?
Okay. It's going to be hard to comment, but I will say that if you look at the construction, I want someone to implement it to really see the overhead. Although just looking at how I have to implement the circuit, I need to embed arithmetization of one prime to another prime for elliptic curve operations, I think the overhead, the margins are going to be a lot. But that should not deter people from trying to implement this. But just to maybe give a rough idea of, not the construction, but where it comes from functional encryption is that, so functional encryption, again, just like witness encryption, if you want for general purpose polynomial size computation, the only way we know is to do it from indistinguishability obfuscation. But a very restricted form of functionality is an inner product. Okay, I take two vectors, I want to compute the inner product. Can I do this under, can this be the function, and can I do this under functional encryption? And there are constructions, actually there are, I want to say, feasible constructions to do this. Now, this recent work that has shown that we can implement this functionality that Wei said, where if a certain condition, and this condition really you can think of it as verifying a zero knowledge proof, then I will sign a particular message. And this can be, again, translated into whatever functionality you want in the underlying blockchain layer. And just using this inner product functional encryption, you can construct one that can do this functionality, which is verify a certain kind of proof and then sign, say, under the Schnorr signatures which are needed for the Bitcoin protocol. Again, I want to say that the fact that these primitives can be useful for these is not surprising. These are like really very strong primitives that have, really a vast range of applications, but discovering where it is practical and feasible is still really an ongoing research.
Got it. So perhaps let's zoom out a little bit more to DEAC, the concept of DEAC more broadly. I think one way to look at where we can apply programmable cryptography is wherever a TEE has been used, right? So there's two angles to this. If a TEE is currently needed, can we remove that reliance on the TEE? And where else can we insert this trusted execution environment where we could actually use cryptography, right? And so can you actually comment on the difference between trusted execution environments, trusted hardware, versus programmable cryptography using obfuscation?
So as I mentioned before, right, TEE can give you what is called, close to what's called a black box obfuscation. And that's a technical term, but what it really means that it can give you access to just the input-output behavior of a functionality. Now, in general, if you want to realize it without any hardware assumptions, it's impossible. So indistinguishability obfuscation cannot serve as a replacement for TEEs. But I think maybe I want to make a spiel here of a larger point in general in this area, and also probably because of my sort of background here, is that when we all studied like zero knowledge and MPC, actually MPC in my mind can solve most of the things that we want. Now witness encryption, functional encryption, IO, all of these help to address certain adversary or certain certain kinds of attacks on the protocol. Actually, it can minimize interaction, it can help you interact with smart contracts better, etc. But I think if you look at it, MPC on its own can solve a lot of these. So when we think about these primitives, we also need to understand, is it that this attack vector is why these primitives are crucial? Again, I mean, I don't want to comment on that, but this is something that people have to understand. And even when you have to implement things like witness encryption and functional encryption, there is going to be a DKG component. The DKG assumption is no different than what you will have to make for MPC. From a security standpoint, you're going to say, hey, up to n-1 of the parties are going to be corrupted, or up to like half of them are going to be corrupted. So from, at least from a number of collusions, etc., these, like when you compare MPC and witness encryption and functional encryption for these things, you can't put them on the same place. And I'll also say that MPC today is far more efficient than it was, I want to say, like when I started studying MPC. So when we are thinking about these applications and these great primitives, I would pose this question that, hey, can we devise first an MPC solution? Can we deploy it? Can we see, is this enough? Like, is this already going to give you certain meaningful privacy guarantees? Yes, at the cost of maybe some denial of service attacks. But I do think that in terms of even realizing the potential that we are seeing of these things, to look at MPC.
So is it correct to say that there's a spectrum from trusted, something that requires a lot of trust, to something that's very trust minimized, where we actually rely on math? In the middle is MPC, right? MPC still relies on mathematical assumptions, but we actually ask certain nodes to be honest, right? And there's ways to hold them to be accountable if they behave dishonestly, which is actually a quite open research area. The notion of accountable MPC, which I think is actually within the same category of programmable cryptography. We should do applications first using more trusted, well battle-tested primitives, and then move to things like obfuscation. So maybe in the last couple of minutes, let's explore the actual feasibility of these more advanced primitives. I think the first result that's peer-reviewed and accepted by the wider cryptographic community that says IO obfuscation is possible came from 2021, right? And can you comment on what has happened since then? Has people implemented this primitive, and what is the performance like?
Yeah, actually, when I was doing my PhD classmate, Hui Jia Lin, she is one of the authors of this 2021 paper that solved indistinguishability obfuscation. But one needs to actually understand, what did they solve, right? When you say that, can I realize indistinguishability obfuscation, it was like, at least a decade back, they showed the first candidate construction based on multilinear maps. But then after that, there was this huge cycle of people, trying to define what is the security of multilinear maps. There were constructions, they were broken. There were constructions, they were broken. The obfuscation construction itself wasn't broken, but the assumption was broken. So really, in the theoretical community, it was about trying to find the falsifiable assumption based on which you can construct obfuscation. And this JLS paper in 21 came up with the first set of falsifiable assumptions. And I just want to say, as a cryptographer, for us, our bread and butter is about getting things using falsifiable assumptions. And that was the huge breakthrough in JLS 21, that you could construct obfuscation based on falsifiable assumptions. But if you look at this construction, it requires 4 different things. LPN, LWE, bilinear maps, like several cryptographic assumptions went into constructing this. And now since then, what people are trying to do, which again is one of the other sort of really motivating questions in cryptography, is to minimize the cryptographic assumptions. You don't want to assume 4 different things. And a more recent line of work is trying to get another flavor of a single assumption, which is a lattice-based assumption, to construct obfuscation. There are, again, candidates, but it's kind of going a little bit in the cycle of multilinear maps, where they define something, it gets broken, they define something. But, this is a cycle that, theory people are used to in terms of these constructions. But just to, wrap up with the practical feasibility of this, we are far from obfuscation being practical. I want to say that there was a paper, I forget now, maybe 6 to 7 years back in crypto, where they did construct an obfuscation that could do 5 operations. And I mean, like, really 5 gates of computation, and that took like hours to run using multilinear maps. And that being said, definitely research should still go into making these things, both reducing the assumptions, but also trying to find out, in a limited form, can these things still be practically constructed.
So, a counterpart to that is, if you look at 10 years ago, maybe 15 years ago, people said the same thing about FHE and ZK, and the landscape has really changed. Do you think the same thing will happen for obfuscation? And are there enough cryptographers actually working on this?
That's a great question. I will first say that I will not bet against cryptography. I know all the researchers in this field. They're making tremendous progress in doing this. But will it accelerate as much as zero knowledge and MPC? I think that's a little bit of a different question. It really comes from, is the community invested in solving that problem? Let's take the Bitcoin signing example. You don't have this particular opcode that you want that will allow you to verify zero knowledge proofs. In my opinion, well, if the Bitcoin community are willing to bring opcat, you can now verify zero knowledge proofs. That is, to me, an easier path towards that particular goal than trying to make a functional encryption problem solve.
Well, I think